Hi, hello students. Today we'll discuss about impedance matching networks. So here the objective is we are going to design an impedance matching network. It is going to match the impedance between two circuits or two networks in a microwave communication link. So why the need for impedance matching? That is, if the impedance between source to load, whatever the equipments are connected, everything whose impedance should be equal with the characteristic impedance in order to deliver maximum power from source to load. So the main objective is, with the maximum efficient transmission, we need to match the impedance between source to the entire equipment, whatever is connected between source and load in any kind of communication link. So that is the objective. So today topic we will discuss that how to design impedance matching network with the help of a Smith chart. See here, I have shown here it is a Z-Y Smith chart. The Z-Y Smith chart is nothing but it is a combination of both the impedance as well as admittance circles are available. So in what way it is different and how to plot the impedance and how to measure the impedance matching networks, all those things we will discuss now. Right. See here we have two different colors where the Smith chart is represented with red color circles and one is blue color circles. Here the red color circles, whatever is coming from here, it is called as all these red color circles are impedance circles, where Z is equal to R plus J plus or minus JX. R is resistance circles in the origin, and the upper part it is plus JX reactance. The lower part is minus JX, it's also reactance. So all the red color circles are representing impedance. All this side from left hand to right hand side, the circles coming here, it is represented in blue colors. All these are called as admittance circles. So circles which is passed through the origin, that is called as conductance circle, that is G circles, and the upper half is minus JB, that is B representing susceptance, and the bottom is plus JB. Similarly here it is plus JX, here plus minus JB. In the lower part it is plus JB, this side the lower part is minus JX. Okay, so these are the representation of circles. Right now we will discuss that with the help of a problem. We will move on to that how to finalize and how to bring the values of all those things. So see here in this case, so we will take one problem. The problem is design two matching networks to match ZL is equal to 10 plus J10 ohms to a 50 ohm transmission line. Specify the values of inductance as well as capacitance at a frequency of 1 GHz. So this is the problem, right? So here the load impedance is given 10 plus J10 ohms, whereas transmission line impedance is 50 ohms. So from these two values we can understand that these two values are not equal. So there is a impedance mismatching. So in order to deliver maximum signal between the transmission line to the load, we have to find a suitable network. The network which is consisting of two components, one is inductive and another is a capacitive component, and that should be operated with the frequency of 1 GHz. So we have to find out what will be the configuration of such kind of impedance matching network and how it looks like and what are the values, how to find all those things we will discuss, right? Take for an example, this ZL is equal to 10 plus J10. So we have to find out the normalized value first of all. So the given values are load impedance, Z0 frequency, and we have to find L and C. So we have to find out the normalized load impedance by taking ZL by Z0. We have to divide the given load impedance by transmission line characteristic impedance, that is 50. So 10 plus J10 by 50. The answer is 0.2 plus J.2. So this is the normalized impedance because the given Smith chart is a normalized Smith chart. So we have to find the normalized value. So first step is we are going to plot this value in the Smith chart. So we will come to the Smith chart now. So I am going to zoom for your convenient. Right. So see here 0.2 plus J.2 I am going to represent. Here it is 0.2 circle is this, J.2 circle is this. So we are going to mark here, that is the given normalized load impedance is here. I have marked over here, right? So this point representing the normalized load impedance, the 0.2 plus j0.2. I am marking over here. This dot is representing the normalized load impedance, right? After that, the transmission line impedance is 50 ohms. So if you have divided 50 ohms by characteristic impedance 50 ohms, 50 by 50, it will be 1. So I am going to represent the transmission line impedance. The 1 is coming over here. So this is the end point. This is the load impedance. So the next step is I am going to draw the unit circle. So the unit circle is the circle which crosses the middle point 1. So here it is 1 representing the impedance is perfectly matched. You can say that the VSWR is equal to 1. It says that the digital impedance is matching, right? So through this I am going to draw the unit circles. So in the through this one we have two circles. One is impedance circles, that is red color circles. I am going to make it as a dotted line. So we have to complete this unit circle. Then I am going to mark this blue color circle, that is called the admittance circle. So completely I am going to draw the unit circle of both the cases. Next I am going to trace from this point. Okay, so I am going to calculate what are the values of what will be the configuration of the circuit and what are the values, how to find all those things we have to calculate, right? Right. So first we will move. I can move from this point to the middle one by two ways. One is through the upper cycle or through the lower circles. So through the upper circle or lower circle I can take. So either you can take this upper portion or you can take the lower portions. The values will be changed, configuration will be changed. So you can find out the values for the two circuits. So through the upper portions, one circuit you will get that is going to match the impedance, or through this lower part you can take another configuration of circuit that is also going to match the impedance. So either you can take through upper portion or through the lower portions, right? So if I move through upper portions, I can trace my point from here to here, and through this point I can move towards the middle. Okay, so every path will give one value. So we have to check what kind of value is this, what kind of circuit is this, that is later we will discuss. And similarly in the lower portion I can move towards this, and where it cuts over here then I can turn towards the middle point. So I have two paths through upper portions, two paths through the lower portions. Now I am going to find out the values. Okay, for that, see, take this example. Yeah, here we have two circles. This is impedance circles, this is admittance circle. Okay, so if the impedance circle, if you trace towards upper portion, that is called as inductance. So upper tracing will give inductive value, lower tracing will give capacitance value, right? So here, see here, if we trace like this, it will give L. Similarly, if we trace in the upper portions, it will give L. If we trace in the lower portion, it will give C. Similarly, if I trace in the lower portions, it will give C. But what is series and shunt? If you trace on impedance circle, it will give series connection. If you trace on admittance circle, it will give shunt connections. Clear? So if you trace like this, in this path, it will give upper portion will give inductance, and since it is an impedance circle, it will give series inductance. Similarly, we have to find series capacitance, series shunt capacitance and shunt inductance, like that. So see, we will move on to the Smith chart now. So for example, if I trace from here to here, I am moving in the upper portions, but what is the circle? The circle is red color. It is the impedance circle. So impedance circle, series connection, upper tracing L. So it will give series inductor value. Similarly, if we trace from here to here, it is admittance circles and it is the lower portions. Admittance will give shunt, lower is capacitance. So shunt capacitance. So this first configuration will give series inductance, shunt capacitance. Okay. Similarly, the lower portions, if we trace here, this is series connections, but lower means capacitance, series capacitance, and this is upper portions, inductance, admittance circle, shunt inductance. Okay, so these two combinations we can get. So after calculating the values by taking the difference between this is the impedance, we will take this inductor value, and from this impedance to, sorry, for this admittance to this admittance, we can take capacitance value. Similarly, by taking the difference between this point to this point, I will get capacitor value, and from this point to this point, the difference if we take, I will get upper half inductor value, right? So by taking the difference between these two values, I can able to construct the circuit diagram like this. So these are the configurations. So this is the one configuration, this is the another configuration. These are going to match the impedance between the load to the transmission lines. So thank you.